when we have particles connected together, we can look at it as a whole system or look at either of the particles individually. So look at the forces on the whole system or look at the forces on just one of the parts of the system by itself. In the first question, we've got two particles, P and Q. Their masses are 5 kilograms and 2 kilograms, and they're connected by a light, so no weight, inextensible, so the tension is the same throughout the string. Particle P is pulled by a horizontal force of 30 newtons across a rough, so friction, horizontal plane. So let's draw a horizontal plane. We've got P being pulled by a force of 30 newtons, and it's connected to another particle called Q, and there's going to be a tension force. So P is 5 kilograms, a tension force pulling P back, but that same tension force is going to be pulling Q forwards. The frictional forces are 10 newtons and 4 newtons. So 10 newtons resisting the motion of P and 4 newtons resisting the motion of Q. And then if we're going to draw in all the forces, we've got the weight, which is mg, and the normal reaction, which just balances it. So the force of the ground back on the particle, so it stays, it doesn't move up, and it doesn't go through the ground. So forces up must equal forces down. We need to find the acceleration of the particles and the tension in the string. So if we look at the whole system, we are going to eliminate the tension because the force, there's a forwards force and a backwards force, and they cancel out. So for the whole system, F equals ma. So the resultant force is forwards, which is 30. Take away forces backwards, which is 10 newtons and 4 newtons, so 14 in total, equals the mass. So the whole system, 5 plus 2 is 7 kilograms. The string's got no weight, times acceleration. So 16 equals 7 times A. A is 16 over 7 meters per second squared. So now we know the acceleration. We need to find the tension in the string. So if we just look at Q, just look at the forces on Q, F equals ma again. The force forwards is T. Force backwards is 4, and that's equal to mass, which is 2, times the acceleration, which we now know is 16 over 7. So we can get tension by itself by doing 2 16 over 7s plus 4. 2 16 over 7s plus 4 is 60 over 7. So the tension is 60 over 7 newtons. One for you to try. See if you can give it a go. So again, we've got two particles, P and Q, connected by a light inextensible string. So this time P is 3 kilograms, Q is 2 kilograms. So tension is going to be pulling P back and pulling Q forwards because P is being pulled along by a 30 Newton force, and the friction is 15 newtons and 10 newtons this time. So if we look at the whole system, F equals ma, we can find the acceleration. So forces forwards, 30, take away forces back, 15 and 10, so 30 minus 25 equals the mass, which is 5, times the acceleration. So 5 equals 5a, a is 1 meter per second squared. Now we can look at just the forces on P or just the forces on Q to find the tension. So again, F equals ma. This time we'll do just Q again. So T minus 10. So if just for Q, the force forwards is T, the force back is 10. So T minus 10 equals 2 times the acceleration, which is 1. So T minus 10 equals 2. T must be 12 newtons. Newton's third law of motion states that for every action, there is an equal and opposite reaction. So this is what I was talking about with the block on the ground. We've got a 3 kilogram mass, which means the weight is 3g, 3 times the acceleration due to gravity. But for the blocks pushing on the ground, there's an equal and opposite reaction. So the ground is pushing back on the block. So an equal and opposite force back on the block from the ground. So now we've got 3 laws of motion. Newton's first law of motion was that an object will remain at rest or remain with a constant velocity unless it's acted on by a resultant force. The second law of motion was F equals ma, and the third law of motion, for every action, there's an equal and opposite reaction. Here we have another question. A light scale pen, so it's light, that means it's weightless, is attached to a vertical light inextensible string. The scale pan carries 2 masses, A and B. The mass of A is 1 kilogram, the mass of B is 2 kilograms, and the scale pen is raised vertically with an acceleration of 1.5 meters per second squared. So there's a tension in the string, which is pulling the whole thing up with an acceleration of 1.5 meters per second squared. If we look at the whole system, the normal reactions, the force of A on B is going to be the same as the force of B back on A. The force of B onto the scale pan is going to be the same as the force of the scale pan back onto B. So those normal reactions are going to cancel out. All we're actually going to have is the 2g, the weight of B, and the 1g, the weight of A. So the only forces for the whole system is T, and then the weight, which is 3g. So if we do for the whole system, F equals ma, T is the force going up, take away 3g, which is the force going down, that's equal to the mass, which is 3, times acceleration, which is 1.5. So the tension is 3 1.5s, which is 4.5, plus 3g. Newtons, in terms of g, we can also give it as a decimal as long as we only give our answer to 2 or 3 significant figures. So we get 33.9 newtons. Find the force exerted on B by A. Remember, the force exerted on B by A is going to be the same as the force exerted on A by B. So it would be easier to just look at the forces acting on the top one, on A. And let's draw a picture from A's perspective. So we've got a 1 kilogram block. It's got a weight of 1g. And there's a normal reaction, which is the force on A by B. And it's accelerating up at 1.5 meters per second squared. So if we get F equals ma, the normal reaction, which is our answer, minus g equals 1a, which is 1.5. So the normal reaction is 1.5 plus g, 1.5 plus 9.8 is 11.3. So 11.3 newtons. And part C, find the force exerted on B by the scale pan. So the force exerted on B by the scale pan is the same as the force exerted on the scale pan by B. So if we just look at the scale pan, we've got a force T going up, and then we've got some force F, some force, probably shouldn't use F, some force acting down, which is the force exerted on the scale pan by B, and it's accelerating up at 1.5 meters per second squared. So F equals ma, the tension is 33.9, minus this force equals mass, which is 0. The scale pan's got no mass, so 0 times 1.5, which is 0, which means the force has to be equal to the tension, so it's 33.9 newtons. Okay, we have another question. Try and give this one a go. So a light scale pan is attached to a vertical light and extensible string again. So we've got two masses, A and B, 2 kilograms and 3 kilograms, and it's raised vertically with an acceleration of 2. So the acceleration is 2, and if we're looking at the whole system, it's just the weights and the tension. We don't need the equal and opposite reactions the masses will have on each other because they are equal and opposite. They cancel each other out. So for the whole system, F equals ma, tension minus 5g equals 5 times 2, which is 5, which is the mass, times the acceleration, which is 2. So the tension is 10 plus 5 times g. 10 plus 5 times g, or 59 newtons. Find the force exerted on B by A, but that is the same as the force exerted on A by B. So let's just look at A. It's a 2 kilogram mass, so its weight's 2g, and the normal reaction is the force on A by B, and that's the same as the force on B by A. They're equal and opposite. So R minus 2g equals 2A, which is 2 2's. So that normal reaction is 4 plus 2g, and 4 plus 2 9.8s is 23.6. So it's 23.6 newtons. Find the force exerted on B by the scale pan, and that again, that's the same as the force on the scale pan by B. So the scale pan looks like this. It's got a tension force going up, and there's some force exerted on it by B. So the tension, which is 59, minus this force, is equal to the mass, which is 0, times the acceleration, which is 2, but 2 zeros are 0. So the size of the force must be 59 newtons. So the force exerted on B by the scale pan is 59 newtons.